Thank you. Merci pour l'invitation. So I want you to start by thinking of a tetrahedron. And the vertices are moving. So the points are moving in space. And of course, occasionally it's a codimension 1 phenomena. So one point will go through and the 4 will become coplanar. Occasionally. It could happen. Or the tetrahedron might just spin around and rotate. So I'm interested in when I will also use the word degenerate. So they degenerate. So, but I have to tell you how they're moving, and they're going to move by Newton's equations. So the moving. So we write down the, so they're point masses. They're punctual. Hard to read here, so thank you. Everybody's here. Okay, so I'll go here. Okay, so the motion. So I have QA of t. K equals 1, 2, 3, 4. I'm just going to write down Newton's equations. So the QA of t are in R3. So the mass times acceleration is the force. And so the MAs are, of course, they're just parameters. Dot is ddt. 2 dots is 2 ddt's, so second derivative. And the force, each mass is pulling the other. So force 1, 2 is looking like this. Force 1, 3 is like this. All I really need is that they're attractive, an attractive force in this direction. But I'm going to start with Newton's version of what the forces are. So the FAB, there's a constant of proportion, just a constant in front. So this is gravitational constant, masses, and then I write, so the R's are the distances of the lengths of those edges. Wait a minute, I want to do it like this. I'm going to do it like this. Okay, this is a unit vector along the edge, and this is how strong the force is pulling. So it's a way of saying this guy is pulling this one in this direction, 1 over r squared force. So those are Newton's equations. And just for notation's sake, I will put all the Q's together. So that's a vector in R3 to the 4th power. But it's going to be very helpful for me to think of this as a matrix space. So I'll think of the Q's as column matrices. So this is I think it's 3 by 4 matrix. That will be useful. So let's talk about the symmetries. Before I write down the equation, I want to just remind you something about mechanics. Can you see in the back these words? Symmetries. And the symmetries are related to conservation laws. So if I have a solution, I'm just going to summarize it QA of t, I can translate it. So that's translation. And that has a symmetry called linear momentum. I'll just write it down. And a conservation law associated to it. So somehow this is usually often called Noether's theorem, the connection between symmetries and conservation laws. And then I can also take a solution and simultaneously rotate everything, huh? So that's a rotation. And so rotation. And I can finally, there's more symmetries, but we'll just talk about these ones. I can time translate. Usually with time translation, we associate energy. This is the one that's important. The conservation law associated to rotation is angular momentum. It has this expression. So this is called angular momentum, momentum cinétique, je crois, en français. Angular momentum. So symmetry is a group operation that maps solutions to solutions. It can involve time. Conservation law, so it's a function of Q, and it's a function of position and momentum, so that if I insert a solution into the conservation law, it's constant. So these are things that don't change along solutions. So we probably all know about energy conservation. You also have angular momentum, linear momentum. I'm mostly interested in setting the angular momentum to be 0. So let me write down let's see, I need a little bit more information. I think I just need a definition. Un autre or no? Okay. All right. So definition, solution is bounded, which I'll abbreviate like that, if there exists a positive constant such that for all time the interparticle distances, I maybe forgot to write down what those were, the interparticle distances are bounded. So what I'm trying to say is the tetrahedron cannot get too big. It stays bounded. There's just some bound, okay?
In this case, you assume no collisions?
So that has to do with the for all t.
Okay.
So for all t in interval of, and I'm not going to care. If there's a collision, we'll just stop, okay? So here's the theorem. If a solution is angular momentum 0 and is bounded, and defined on an infinite time interval, and its interval of existence is infinite, so it could be a half ray, okay? Then there exists infinitely many coplanar coplanar events. It becomes coplanar over and over again. Okay, so that's the theorem that I want to explain why it's true. But first, so that's the goal, is to, and for me the most exciting part is how the proof came about. That was, but let me tell you why I was interested. So I should say when I prove it. For a reason that you'll learn soon, I'm going to call this theorem 3. And and so I did this, and I just did this. I did this in September. I'm still writing it up. So, so motivation. So for the motivation, I'll just look at triangles. So the QA are going to be in R2, A equals 1, 2, and 3. Everything is the same. Everything is the same. It's just the vectors are in R2 instead of R3, and there's only 3 of them. And then what's degeneration? Goes through and becomes collinear. So that's what a degeneration is. So you can maybe guess the theorem 2 if a J equals 0 solution to the 3-body problem in the plane, the 3-body problem in R2 is bounded. So the boundedness still makes sense. Then there exists infinitely many collinear instances. There exists, and has interval of existence infinite. Let's just write it. Okay, for example, it's at least that big. Then there exists infinitely many collinearities. Okay, so it goes collinear over and over and over again. And this was important for me because every time it goes collinear, I can talk about what mass is going between what mass. And in that way I get a symbol sequence. So this gives you symbol sequences. By just saying what order, these are eclipses. You can think of them as one planet blocking the other. So these are eclipse sequences. So this I did in, I think it was 2002 or 3. So there's a big gap between this there, and so I'm going to talk a little bit why such a big gap. So this is half the motivation. And the other half of the motivation, I have to tell you a bit about the proof of this theorem. So I'm going to go into a little bit of the proof, and then we'll modify the proof to get this theorem, and I'll let you guess at what theorem D is for D equals 4, 5, 6. Okay? Well, so there's a, right? This is 2 instances of a theorem that works generally. We'll get to that. So let me tell you a little bit about the proof. Oh, I have a motor, do I? Am I hurting anything by using it? Don't know. Okay. Let's see.
In Theorem 3, is there a formula for the density of events in time?
For theorem 3, yeah, there's not an explicit formula, but there's there's an upper bound. So I know they happen at least so often. And I'll get to that. Thank you. Yeah. So motivation.
And also for theorem 2, I mean.
It's going to be the same bound for the theorems. Yeah, same upper bound. Yeah. Okay, so the main idea of the proof, so the rest of the motivation is going to come from this side. So I want to use these symmetries to push the differential equations down to the quotient space. And the quotient space is going to work a lot better when I set j equals 0. So for people who know, I'm doing symplectic reduction at j equals 0, but I'm going to do it in a Romanian fashion, and it's going to work better. So that's basically what I'm doing. So I think, yeah, let's start. Okay, so we have the configuration space. So I might as well jump to the theorem D. No, let's stay like this. So the three-body configuration space. So three-body configuration space. It's this space of 2 by 3 matrices. It looks like R2 cross R2 cross R2. And these together form a symmetry group, G SE2, looks like R2, and rotations and some funny semi-direct product. So it's rotations and translations. And the equations, Newton wrote the equations to be invariant under these symmetries. He knew Galileo's work, so he explicitly wrote them to have all these symmetries. So natural thing to do is try to push them down to the quotient. So push the equations, which I'll just call N for Newton, push N down to the quotient, M2, 3 mod this group. So what is this? This is, because I'm going to use it for higher, I'm going to change these integers. Let me just give it a name. I call this shape space. So in this particular problem, why is it shape space? It's congruence classes of triangles, right? It's actually oriented congruence classes because I'm not allowing reflections. I was careful to not allow reflections. So it's shapes of triangles. So I'm going to now give you a little sketch of why this is the same thing as R3. So that it's three-dimensional, we all know, because 3 sides determine a triangle. That it's actually homeomorphic to R3 is a bit of a surprise. At least to when this was most of my work in the three-body problem is based on this one fact. So let's see why this is true. Well, I'll just kind of do it in a sloppy way, just to give you the idea. So what am I supposed to do? I'm supposed to take this, and I'm supposed to divide by R2 cross SO2. Yeah? That's what I'm supposed to do. So what I'm first going to do is just divide the R2s. Okay? And then I get, and each R2 is a C, That's a C. And this is an S1. So this is the same as C2 mod S1. And now if you've ever seen the hop vibration, those formulas for the hop vibration actually define a homeomorphism between this space and R3. So, so that's why the quotient is R3. But now I'm going to draw this little cheating step here. This is just fixing the center of mass to be the origin. Okay, so I'm going to draw a picture now of this space. Because I want to explain a little bit of the theorem's proof, this theorem's proof. Okay. So blackboard is R3. So far, no structure. That's triple collision. All three of them have collided. The origin is triple collision. Triple collision is a degenerate triangle. It's sitting inside the collinear states, the degenerate states. Inside the degenerate states, there's three special rays. They're the singularities of the potential. They're where Newton's equations blow up. You can have 1 and 2 collide and 3 be over here, or 1 and 3 collide and 2, or whatever's left, 2 and 3, okay? So you have three distinguished rays. 1, 2, 1, 3, and 2, 3. Now, what do these triangles? A triangle here looks like 2 and 3 on top of each other and 1 there. So certainly it's collinear. The triangle's degenerated to 2 vertices coinciding. This direction here, I want you to think of this direction as signed area. Okay? So when the signed area, right, if I put an orientation on the plane and a labeling of triangles, that guy has positive area and this guy has negative area, huh? So there's a signed area. So the signed area is 0 exactly at the collinear states. And what does the theorem say? The theorem is saying that signed area is oscillating. So the way, right, the key to getting this, maybe I should throw the potential in. I think I'd just say it in words, and if people want me to write formulas, I will. So I'm going to tell you a physical way to think about the reduced dynamics, and I'll write down formulas if I need to. Downstairs, so I keep talking about upstairs and downstairs. You have a map from the full configuration space to the shape space. So I'm going to call this SH for shape. And in this case, the fiber's the group, huh? Okay? So if the angular momentum is 0, if J equals 0, when I push down Newton's equations, it has this simple description. A point here represents a congruence class of triangles, but I forget that. I just think of it as a point in R3. And what are the forces acting on it? It's acted on by a potential force that's attractive, and the sources of the potential force are these 3 rays. So now I want you to think about this situation. You've got 3 rays on the table and an attractive force and this thing here. Well, of course it has to be, it's pulled to the table, right? And once it goes down to the other side, it comes back up. So it keeps oscillating back and forth and back and forth. The only thing that can stop it is if you give it too big of a kick this way, and then it's going to become unbounded. So as the motion is bounded, it's just going to oscillate back and forth across the table. And that's what the theorem says. So that's the physical intuition. I got that from a guy named Mark Levy. I tried to explain the way I think about this problem. He's very much, you'd have to meet him to believe him. But he said, well, Richard, if that's true, the explanation you gave me, then this theorem has to be true. So he just guessed the theorem. The proof took a lot longer, but here's the idea. What you do is, using that physical intuition, you derive a differential equation for the second derivative of the area that looks like this, where G, all you really need to know about G is that it's positive. G depends on everything. It depends on the full Q, well, it depends on the shape and the shape derivative, okay? So it depends on many variables. It doesn't let you solve the equation explicitly, but it gives you enough information. But essentially the idea is you're going to compare it with a harmonic oscillator. So you pretend G is a constant. This is a harmonic oscillator. It just goes up and down. So that's the basic idea of the proof. Okay, so that's half the motivation. So now I want to tell you the other half. So where am I going to put it? I'll put it over here. Okay, so in August of, I'm on sabbatical, and I know a physicist named Robert Littlejohn, and they invited me to his birthday his disappearing conference, his retirement conference. So he was in my talk, and my talk was all done. I talked about three body stuff, and he raised his hand and he said, "You know, Rich," nobody calls me Rich except him. "You know, Rich, the shape space for the four-body problem in R3 is R6. That's what he told me. And I've been working on this for 20 years. I said, I didn't know that. And okay, so look, here I just sketched the idea that just hit my head immediately. Replace the blackboard by R6. Replace that plane by the degeneration locus. It's the same picture. It's got to work. Okay? So let's fill in with some equations what I just said. So we just do the same thing. Okay? So let me do, I change this to a 3 and a 4. Huh? And then this becomes 3, 3, 3, and let's, okay, this becomes a space of square matrices. When you do this crossing out, you get that this is 3 by 3 matrices, mod the action of the SO3, I'll talk about how it acts in a minute. And then the theorem becomes that this is homeomorphic to R6. So that's what Littlejohn told me. Okay, so the same thing works for D plus 1 bodies in RD. Same thing, exactly. So we might just want to switch to that right now. Okay, but let me tell you what screwed me. So that was in August. And then I spent a solid month trying to do this. So I'm going to give you the outline of the whole rest of the proof, and then the rest of the talk will be filling it in. So here was the idea. Okay, this is signed volume, huh? everybody knows how to compute the signed volume of a tetrahedron with a triple product. This is this is now the coplanar locus. It is an R5, but it has non-smooth points, unfortunately. This is where the volume is 0. Okay, so I should do this, huh? Right? That's what I should do. Didn't work. I spent a month on it. I really, really worked on it. I couldn't do it. Finally, I kind of understood why it wasn't working. And I replaced the signed volume by the distance from coplanarity. So replace volume by distance. Now, okay, at this point you should ask distance with respect to what? I haven't given you an inner product or a metric. But once I did that, and I call this signed, so I replace signed volume by distance, I call it S, and then everything worked. Everything worked. So the rest of the talk is explaining where the distance comes from and how I did the computation. Okay? Questions?
So it's a signal distance, positive and negative.
It's important. I want it to be signed distance because otherwise it's like absolute value. It's harder to differentiate. Okay. Other questions?
What you need really is to have a hypersurface. The fact that it's R6 is...
I just need a hypersurface. That's right. You're exactly right.
Distance to the hypersurface and
Yeah.
two pieces.
Yeah, that's what I need. Yeah. So, okay, so now what I want to do is now start the formal structure of the proof. So you kind of see how it fits together. And I'm going to just be a little bit more general here. Partly because it's no extra work, but I think maybe we learn more. So let's take n-body configuration space. So we have a whole bunch of copies of RD. So these are n-bodies in RD. Okay? Newton's equations are the same. Symmetry group is SED. It's actually the Galilean group, and a little bit bigger, but it's at least that big. That's the part I care about. So it's the orientation preserving isometries of RD. That's a symmetry group. So I can try to push down to here. And now let's do this step a little more carefully. So we're going to do it in 2 steps. And I will want, I'm mostly interest in n equals d plus 1. But I just do it this way for a second, and then I specialize. Okay, so the 2 steps are first, just do the quotient by RD. You can do that by fixing the center of mass. Fixing the center of mass is D, linear equations, so it gets rid of one variable. You get md n minus 1. Okay, so I first do that quotient, and then I do the quotient by SOD. So I'm going to do so that's my shape space, and then the theorem, or I'll just call it a proposition, but maybe it should be called a theorem. If n is d plus 1, this shape space is homeomorphic to R to the d choose 2. The book I know where that appeared in is a book called, it's called Shape Space. It's by a statistician named Kendall. And he knew this probably in the 70s or 60s. He's interested in archaeology, and in archaeology you don't know how the bones are oriented in the tomb, huh? So you have to worry about that. Okay. So we're going to use this. We're going to push down Newton's equations, and I want to explain a little bit about how that works. Right. So I need Newton. I think I'll start by writing out the energy. Conserves the energy, which I erased, but it's usually written this way. Kinetic, which just depends on the derivatives and the potential. And the kinetic looks like this. I'll call it V. Kinetic of a velocity V is 1/2 of an inner product, and this we call the mass inner product. It's an inner product on the configuration space, and it looks like this. Okay? So that's the kinetic energy. So in other words, I'm thinking of the kinetic energy as an inner product, or a metric, huh? So if I want to think, so metrically, I have this Euclidean metric. Okay, I think it's time to make d plus 1 to be n. Okay, so I do that. Then n minus 1 is md. Nice space, square matrices. And then the degeneration locus this is where the determinant is 0. So now this is a matrix space. And this locus, the degeneration locus, is where the determinant is 0. So now Q, I've reduced by translations, I'm in square matrices. This distance from determinant equals 0 is relative to that inner product. That's how I measure the distance. I'll put a little m just to remind you the masses are involved.
Is distance it's not in the shape space?
Okay, it's the same. It's going to be the same. All right, so I'm going to do the distance upstairs and downstairs. So let's push things down a little bit. I think maybe before I do that, maybe I should say one other thing. Using a little bit of linear algebra, you can write k of q, or k of v, as 1/2 the trace of q transpose q. So in other words, I can change basis to make it look like that. So it looks like the standard inner product on square matrices. So there's a buzzword for doing this in celestial mechanics. This is called a choice of Jacobi vectors. But this should be a v. So I just standardize the metric. That makes my life simpler. So that's the way I'm measuring now. Once I choose that basis, I'm measuring just a standard. But this is the inner product where the orthonormal coordinates are the matrix entries. Okay, so I do that, and I want to tell you what Newton's equations look like. These equations, Newton's equations now look like q double dot equals minus gradient v of q. I have to remember to use the mass inner product to compute the gradient. Okay, gradients, right? Just remind you. If I take dV of a potential and apply it to a vector, I turn it into a gradient this way using the inner product. So so the masses are involved there. I haven't told you what the potential is. The potential is, this is the famous Newton potential. Okay, so that's a rewrite of Newton's equations. That's a rewrite. What happens? I want to push them downstairs. I want to push Newton's equations downstairs to compute. Here's upstairs in my matrix space. Here's downstairs in shape space. Up here I have this form. There's a metric down here. This process induces a Romanian metric. So you declare, so there's a group, I divide, and I declare this to be a Romani submersion. I'll explain what that is in a second. The point is, this thing now has a metric, but it's not flat anymore. So it has a Levi-Civita connection, different from this one. And the equations downstairs look like, let's call it C. Maybe I'll put a V bar just to remind you. Okay, what's V bar? This function is G invariant. The potential is G invariant. So it induces a potential down here. So so usually I leave out the bar. They're the same function. This is a G invariant function. So where, let's call this pi. So C of t is pi of q of t. In other words, I'm just keeping track of this shape. This only works if j is 0. If j is not equal to 0, there's nasty other terms here, and actually the dimension of the phase space jumps. So I don't know how to do it in a nice way when j is not 0. Let me explain what a Romani submersion is, and that will give you also the reason why j is important, and then I can start the computation. If I linearize this picture, I get a picture like this. This is the group direction. So if you differentiate in the group direction, this is often called the vertical space in principal bundle theory. So this is the vertical direction. If I take a complement to the vertical, to the kernel of d pi, any complement's going to map linearly, isometrically down here. There's one natural complement. Take the orthogonal complement. So HQ is VQ perp by definition. What's perp computed with respect to? That mass metric. So theorem HQ is a set of V's such that the angular momentum is 0. Okay? So the horizontal space, to say your horizontal is exactly the same as saying angular momentum is 0. Since angular momentum is conserved, if you start horizontal, you stay horizontal. What about the metric downstairs? The metric, I have an inner product here. I use this linear isometry to put that metric there. So if I have two vectors here, I know what their angles is. They're the same as upstairs. The lengths are the same. The fact that the group is acting by isometries for this mass metric means that it doesn't matter where on the fiber I do this computation, I get the same answer. So a situation like this is called a Romani submersion, and it satisfies the property that the length of a horizontal curve upstairs, is the length of the curve downstairs. If that curve is horizontal, So this is the idea of a Romani submersion. It lets me push things from up to down and go back and forth. Okay, so that's the basic geometric structure. I need to know one more thing to get my computation to work. And that is, I need to know that this thing's totally geodesic. Geodesics that start on it, stay on it. That's completely false upstairs. Determinant equals 0 is a nonlinear thing. Geodesics are straight lines upstairs. But downstairs it's totally geodesic. And that turns out to be important. So geodesics starting on it, stay on it. So I call this sigma. So pi of sigma. The degeneration locus, the locus I want to cross over and over again, is totally geodesic downstairs in the metric that I just described, that Romani metric. Okay. Sigma is clearly invariant under the, I forgot to say that part. Sigma is invariant under the action. Oh, I didn't tell you how the group acts, did I? Action of SOD on square matrices. It's just a square matrix. That's all it is. It's just left multiplication. Because it's left multiplying each position vector. And this is made up of position vectors. It's pretty clear that that action preserves determinant equals 0. Distance was G invariant. This set is G invariant. So S is G invariant. So S maps down to a function downstairs. So downstairs, I have all this structure. I have my S, my sigma, my V, my metric, my Newton's equations. Okay, finally I can compute. All right. I told you the idea. I just want to take the second derivative of this S. That's all I want to do. So let's start doing it. And I have 9 minutes remaining or less. Huh?
More.
More? Oh, this is great. Okay. All right. Where am I going to start? We'll start here. So the basic idea of the proof is you're going to go back and forth between upstairs and downstairs to do things. So to compute d2s dt squared along solution. In other words, I'm looking at s of q of t, and I'm assuming that the q has zero angular momentum. So that's what I want to do. Okay. So let's start with one derivative. Well, in Romani geometry, that's equal to this. But remember, this is G invariant, and I can write Newton's equations downstairs. So this is also equal. I'm going to use the same symbol upstairs and downstairs. Okay, so this is downstairs. This is on shape space. Okay? Now I differentiate again. Well, I'll do it over here this time. This is going to be grad S. Now I have to use a covariant derivative. Did I write down Newton's equations? Yes, good. And there's another term, right? There's two terms when you covariant differentiate. There's a grad C dot, grad S C dot. Let's put in the equations of motion here. So this is minus grad S, grad V at C. I can put this either place. And then I'll keep this one like this. And I'm going to call these terms 1 and terms 2. And there's going to be a theorem 1 and a theorem 2. Both of them satisfy what I want. So theorem 1, grad S minus grad V along a solution is of the form minus S times G1. G1 is greater than or equal to 0. There'll be a theorem 2. The other term, which I'm going to write this way, grad V, grad S V is equal to minus S times some h of VV, and h is a positive semi-definite form. So see, the strategy is the same. I took the second derivative together. This will say that this is equal to minus S times some G, and the G is positive. That gives me my oscillation. But I get a little bit more. I get this one, G1, and, oh, this is strictly positive. That's greater than or equal to 0. And G1 is greater than or equal to if the bound RAB less than or equal to C is in force. So if I've bounded all those things, M is the total mass. Okay? So what this does is it says, just replace, so the idea of the proof now becomes, call this thing a constant, K. Basically, I just replace the equation with S double dot is minus Ks. And that gives me the bound you were talking about, because that's a harmonic oscillator. It tells me there's a 0, and you can say explicitly, there's a 0 at least in any interval this size. Okay?
You have also bound, number bound?
No, the bound the other way, this way.
So that is not
No, you could make that, what happens is the closer they get, the faster they oscillate. Okay, so there's no upper bound. Okay, so this is the third time I've given this talk, and this always happens. I get to the end, and I can prove either theorem 1 or theorem 2. I can't do both. There's no way. Anybody want to take a vote, or you just want me to start one? Anybody prefer 1 to 2? Eve? Anybody care? Okay. Nobody cares. All right. I guess I'm going to tell you the key ideas for both, and I'll get as far as I can with one. So the key idea, again, comes from Romani geometry, and it has to do with a general fact about signed distances in any Romanian manifold. And luckily, I was at this thing I was at MSRI. It was a lot of it was on what they call weak KAM, which has to do with Hamilton-Jacobi. And the simplest instance, well, I'll just state the theorem. Take any Romanian manifold. And look at a closed set. And look at the distance from Q to K, and call that function S. That satisfies a Hamilton-Jacobi equation, which is very simple. It's just grad S equals 1. Now, it does have singularities. There's points where it's not smooth, and I will have to worry about that in the technical part. But just to give you two examples, if I take the x-axis in the plane as k, then the distance, then s is just y, absolute value of y, right? And then the gradient of s is going to be plus minus 1. The reason I do the sign distance, I don't know how to make sense out of the sign distance unless this is a hypersurface. The reason I did the sign distance is because I wanted it to be smooth through here. So the same theorem works for sign distance. So what does Hamilton-Jacobi also tell you? It tells you, so this is Hamilton-Jacobi equation, and people also call it the Eikenol equation. So I need to tell you a little bit about the integral curves of this thing. So let's talk about the differential equation dq d tau equals grad s q of tau. This again works in any Romanian manifold. Assuming I'm at a smooth point of s. These are geodesics, and they hit the closed set, hit K orthogonally, assuming I'm hitting it at a smooth point. So for example, if I look at the sign distance from a circle, I'd go out in radial directions like that, huh? Or the sign distance here, it's even simpler. I'm just going like this, and the geodesics are like that, huh? Okay. So let's start. I use that in both the proof of Theorem 1 and Theorem 2, but let's just do Theorem 1. So the trick is to realize that you're taking is to look at this a little different way. Instead of differentiating S, you're differentiating V. You're differentiating V along the integral curves of S. That's the whole trick. So to do Theorem 1, grad S minus grad V is equal to d tau of minus V of Q of tau, where I'm solving I'm looking at the integral curves of that. So Q of tau, remember, I can do it upstairs or downstairs. It's going to be easier for me to do it upstairs. Q of tau is a geodesic perpendicular to sigma. Unit speed. But why is it unit speed? Because grad S is 1. Okay, so let's look at what these geodesics look like to see how the computation goes. Geodesics in M's a Euclidean space, so geodesics are lines. That's what they look like, just straight lines. Okay, but there's something special about hitting sigma orthogonally. So at tau equals 0, I'm in sigma. So let's assume that I'm at a generic, so I have to break it into pieces, the proof. I'm going to assume at a generic point of sigma. What that means is in the four-body case, I'm actually planar. The four are planar. They're not all four in a line. Those are the smooth points of sigma. When all four are in a line, those are the non-smooth points. So assume i.e. planar if D is 3. Okay, so now let's draw a little picture of what that means. So Q1, Q2, Q3, Q4. The reason I'm drawing a picture is because I want to understand what it means to be orthogonal to sigma. So I want you to think about how you would generate directions in sigma. This is lying in a plane. The easiest thing to do is just vary these arbitrarily in the plane, right? If we just vary them arbitrarily in the plane, you've certainly made a deformation of your shape that's degenerate. You agree? Now, I can take any variation in the plane I want. That means the v has to be in the orthogonal direction to this plane. Every single v is perpendicular to the plane. Okay, now I'm ready to I need that information. So I'm ready to compute. So what I have to do is use that information, and I want to compute d tau of the potential, which was g ma mb rab of tau squared. Okay, it all boils down to different, not squared, just like that. The minus sign can't, so, all right, so I need RAB of tau squared. I need that. So let's write it out. It looks like QA plus tau VA minus QB plus tau VB squared. The important thing is a term cancels. Otherwise, I couldn't do the computation. This is equal to QA minus QB squared plus tau squared VA minus VB squared. And then there's a cross term, 2 tau. OK, the cross term's 0 because this is perpendicular to this. The VAs are all perpendicular to the QAs because V is perpendicular to sigma. The initial velocity is perpendicular to sigma. So the cross terms are gone. They're not there. That makes it easy to compute. And I'll just write down the result of the computation. You could all compute this at that point. I'll just tell you what the answer is, and then we'll stop. I might have written it down. Let's see if I wrote it down. Yeah. So you get that this is equal to minus g tau summation ma mb rab of tau cubed va minus vb squared. Okay, so that's the computation. Okay, now you go back to the Hamilton-Jacobi equation and you say, what is that tau? The tau is the integral that you do. Remember, you're integrating perpendicular to this closed surface. Tau is just s. Tau is equal to s. Minus s, so that's tau. So you have to go back to the Hamilton-Jacobi equation to see that. That's how how you make, it's the same idea of making tubular neighborhoods. If you've seen that proof in Romani geometry, you exponentiate out to make tubular neighborhoods. This is minus s, and then you have this funny quantity. Okay, so that gives my positivity. What about my bound? Well, the bound is a little bit more work, but basically the bound comes because summation ma, this is an identity of Lagrange, that this is another way to measure. This is the total mass times v squared in that mass metric. So this is an identity of Lagrange. There's something I hid from you here. What I hid from you is I'm assuming, I can assume this is 0. That's what I do to do reduction. So I hid that from you. Anyways, you use that, and you get the theorem that I, of course, erased. But you get the theorem 1, OK? And I'll do theorem 2 to anybody who wants to hear it. I'm already out of time. Thanks.